All right, I think it's kind of time. So let me introduce David Rolnick a little bit. So in this session, we will hear from David Rolnick on machine learning in fighting climate change. So David is an assistant professor and Canada CFAR AI chair in the School of Computer Science at McGill University, and then also like the Mila Institute, Mila Quebec AI Institute. He's a co-founder and chair of Climate Change AI and serving as a co-director of Sustainability in Digital Age. So if you don't know David, he co-wrote like one of the paper in the field called like Tackling Climate Change with Machine Learning that was published in like 2019 with like many different people who may know, like Yoshua Bengio. So if you haven't read it yet, like I really encourage you to go through like archive or like the journal to read the paper. So please give a round of applause and welcome David today.
Thank you so much for having me. It's a pleasure to be there virtually. I'm sorry that I can't be there in person. And as I noted for those who arrived early, it is almost midnight here. And so if I fall asleep while talking, that's why. Please wake me up gently. Let me share my screen. Hopefully, can you see this? Yeah, great. I can still see the chat. I can see a little image of people. So if you will like wave, then I might be able to see if there's a question. And my understanding of the structure is that I have about an hour and 20 minutes, and then some time for questions, then a break, and then same thing. Is that correct? Is that right? Yeah, good?
Yes,
okay.
Yes.
Excellent. Okay, sorry, it's just hard to hear sometimes from people further back away from the microphone. Okay. So that is a lot of stuff to cover. I hope you're all ready for it. Climate change. I don't think that climate change needs very much introduction, unfortunately. We're increasingly seeing it all around us. The impacts are felt globally, depending on where I'm speaking to. Everyone is seeing different effects, but they're becoming more common and they're becoming more severe, everything from flooding to fires to storms to droughts and famines associated with them. And it's also worth noting that across geographies and within a geography, climate change often has a disproportionate impact on the most disadvantaged population. It serves to reinforce existing societal inequities. So, for example, in the US, where I'm from, we see that poorer communities get hurt by climate change more. And often poorer countries can also get hurt by climate change more. We need net zero greenhouse gas emissions by 2050, according to the UN's IPCC. I'm going to go into every bit of that in a moment. That is the overall thing that we are working towards, and it requires lots of different forms of action across energy, transportation, buildings, industry, agriculture, forestry, lots of different kinds of action. How does machine learning fit into this picture? That is what we're going to try to address today. And here is an outline of how this is going to go. First, an introduction to climate change, because probably many of you have not engaged much with details of climate change and climate action, and that's totally fine. And this is not going to be a replacement for really in-depth examination of climate change, but it is going to give a quick overview of a lot of the terms and ways to think about things. Opportunities for machine learning in climate action, ways that machine learning applications can be used, several different themes for how machine learning is even relevant in climate action. Research challenges. So ways that there are, that the problems in climate action pose exciting or promising research challenges for people who want to work in machine learning. From physics-informed and robust machine learning to interpretable machine learning and uncertainty quantification to generalization and causality. Go through some example projects next for my own group at McGill and Mila. Talk about the ways that machine learning can hinder climate action, can make climate change worse in addition to making it better. Think about considerations for research and deployment, and then think about broader takeaways and how to get involved. Okay, let's dive in. But first, I realized, sorry, I need to give lots of acknowledgements. This is based, first of all, on a tutorial that I first gave with Priya Donti, who's now a professor at MIT, Lynn Koch, who's a professor at the Hertie School in Berlin for ICML last year. So huge thanks to Professor Donti and Professor Koch, and also to these various other folks who gave their input on the tutorial in its original form. Okay. So with all that said, let's dive into the first component. We're going to start out with an introduction to climate change, both where we are and what we can do about it. So the Earth has already warmed over 1 degree Celsius above pre-industrial levels. I have to specify Celsius for like most Americans, but in the other civilized parts of the world, people use Celsius instead of Fahrenheit. America's weird. The Earth has already warmed 1 degree above pre-industrial levels. Human activities are responsible for this sudden increase. You can see that natural causes do not induce such a change. And the reason for this is greenhouse gas emissions, including carbon dioxide, methane, and nitrous oxide. There are also a bunch of other ones, but those are some of the big ones. Now, this warming has in turn induced major changes in the climate. Now, climate versus weather. Climate is the average weather over 10 to 30 years. So you can think of climate as the long term and weather as the short term. Now, we're also seeing increased extremes in terms of phenomena like heat waves, precipitation, droughts, and hurricanes. So it's not just a question of things getting hotter, we're also seeing other kinds of events that are precipitated by changes in the climate. Now, every unit of greenhouse gas emissions that we put into the atmosphere adds further to this warming and the subsequent changes in the climate. In particular, this plot from the IPCC, that's the UN Intergovernmental Panel on Climate Change, which studies climate change and compiles a lot of studies on climate change. This plot shows how much warming we can expect depending on how rapidly we act. Now, the upshot is that the faster we act, the less warming we'll get. So these are different scenarios, different amounts of warming we can get depending on what we do. For example, hitting net zero greenhouse gas emissions, so overall net positive and negatives from anthropogenic, from human activities, net positive and negative being 0 emissions. By 2050, that is one scenario, and that would limit warming to 1.5 degrees. And that's a goal that the international community has agreed will help avoid some of the worst impacts of climate change. That does not mean we do not have impacts from climate change. For example, we're already, even in that scenario, going to, I believe, lose almost all the world's warm water coral reefs, even in that scenario. And we are not currently going to hit that scenario. So there are a lot of different takeaways you can get from this. One is doom and gloom. Even the best scenario leaves us with catastrophic consequences, but not the most catastrophic consequences. There are other scenarios that really, really are terrible. But you can also think about this as climate change is not an on-off switch. So every bit that we do makes things better. We have a choice between really bad and really, really bad. So how do we actually go about addressing climate change? Several different axes of action. First is climate science. So that means understanding and predicting climate change. The second is mitigation. That means reducing greenhouse gas emissions or preventing them from occurring. And the third axis is adaptation. That's responding to the effects of climate change. And then in addition to these 3 axes of action, there are also different lenses through which you can look at them and frameworks for thinking about it. One of them is climate justice, and that notes that the brunt of climate change's impacts will be felt by the world's already most disadvantaged populations. And for this and other reasons, equity needs to be a central consideration in how we approach climate action. And another framework for thinking about climate action is a co-benefits framework, which is about thinking about climate action holistically, recognizing that it interacts with other societal priorities like human well-being and ecosystem health. If we prevent climate change but kill everybody, clearly that's a bad outcome. So thinking about how we can use climate change to make other things better instead of worse. Given that overview, let's talk a bit more about each of these different axes. So first, climate science. Climate science entails the study of the Earth, the ocean, the cryosphere, which is like ice and snow, and the atmosphere, to understand how climatic processes are playing out in these systems. I'm actually not going to dive into this area further, but there are great tutorials by these folks from NeurIPS in some years back. I do want to dive further into climate change mitigation. And this is, again, strategies that aim to reduce or prevent greenhouse gas emissions. So greenhouse gas emissions, there are several of them: carbon dioxide, methane, nitrous oxide primarily, and they come from many different sectors. So you can see this colorful plot. And there are many different strategies that are needed to reduce emissions that span these different sectors. So let's dive in, breaking into a few different categories. These are the various different sectors we want to think about. The first group of sectors are all about energy-related emissions. And when we think about reducing emissions in these kinds of sectors, we can use a conceptual framework which is called the Kaya identity. Now, the Kaya identity breaks down greenhouse gas emissions into a product of a few different illustrative terms. This is a very obvious equation. Like, clearly this is true, but these terms are useful. Population, service per population, energy per service, and greenhouse gas emissions per energy. So for example, starting with service per population. This refers in broad terms to how much a given person consumes. So reducing the service per population means reducing the per capita consumption. To make this more concrete, let's use the running example of passenger travel in cars. So in this case, the service referring to is the number of vehicle kilometers traveled. There are a couple of different strategies here. They can help reduce the amount of service used per person. That's reduced per capita consumption. So one of these, for example, reducing the number of kilometers driven. Pretty obvious. For example, an individual could move closer to work or work remotely in order to drive less. On a systemic level, laying out cities in such a way that homes and work are close together could reduce the total need for driving. We could also increase the number of passengers per vehicle to reduce the amount of unique vehicle kilometers per person. So these examples are illustrative of some of the broader general levers we have. Those include individual changes to reduce consumption, but important systemic changes and structural improvements also that enable individual and organizational action. So both of these levels. So the next term in the Kaya identity is energy per service. Reducing this term can basically be thought of as reducing waste or improving efficiency. So for example, in the example of passenger cars, you could reduce the amount of fuel that's used for every mile by using a more fuel-efficient vehicle or driving more efficiently, or by switching to modes like biking that still get you where you need to go, but by using less energy. So again, these hint at some general principles. You can reduce waste in terms of how energy is consumed, and you can also reduce waste in how the energy is produced and moved around. So the last major term is greenhouse gas emissions per energy. Bringing this term down means switching to clean energy sources. So in the case of cars, that could mean switching from fossil fuel vehicles to electric vehicles if the electric vehicles are charged on a low carbon grid. Like, you don't want the electricity to be produced by coal to charge the cars, because then you're still producing emissions to generate energy. You could also switch to alternative fuels that can be used within traditional cars, like electro fuels, solar fuels, hydrogen fuels. These are all like fuels that are produced in a carbon neutral manner. In general, that's technology that's still under development. So you should be wary when people are selling these kinds of tech, because they're not there yet. Again, this hints at some broader strategies, one of which is to electrify everything. Take something powered by fossil fuel, make it electric, and charge it using like wind or solar power or nuclear power. The other strategy is to take your liquid fossil fuel and replace it with some clean alternative fuel. So some of the basic ways to think about energy-related emissions. But this is only some of the emissions. Some of the emissions come from land use. So that's primarily agriculture and forestry. And it comes from a few different activities. Land use changes, things like cutting down trees, draining peatlands, for example, to make room for agriculture. Oftentimes, both deforestation and draining wetlands, other things, is for agriculture, not for like timber necessarily. Fertilizer use, ammonia production, which is used for fertilizer, actually accounts for about 2% of global energy consumption. And the application of fertilizer also leads to the release of nitrous oxide, which, as you remember, is another greenhouse gas emission. That's kind of a double whammy: use energy and also to make greenhouse gas emissions. And then livestock also produce emissions, primarily methane emissions from ruminants like cows. Now, it's complex to assess the effects of interventions here, given the complexity of the natural carbon cycle and the many different interactions between climate-related socioeconomic, and natural factors. So, for example, one common climate-related strategy is afforestation, planting trees. This is not that good, generally speaking. Planting trees can capture carbon, can take carbon dioxide out of the atmosphere, but there are a lot of ways in which this is suboptimal. The trees can die often. Like, if you don't keep on maintaining them, they just release that carbon right back up. They could burn if there is a forest fire. If you plant a plantation of trees on an area that was already storing carbon, the carbon in the grassland or the shrubland or the peatland or whatever it was before can release its own carbon. So maybe you don't actually save carbon. You might actually lose carbon. And you don't want to plant trees on land that was being used for farms, because then you have to clear more land to make the same amount of food. So planting trees can be tricky. That was sort of a side note. But there are a lot of different factors involved in actions related to land use emissions. And that's sort of an example of how you might think about it. Lots of economic incentives that can cause different actions to be taken. It's important to think these kinds of factors through and how they interact. So different kinds of strategies that you might think about in land use. You might think about, in the context of natural land systems, strategies like preventing deforestation, preventing trees from being cut down, preserving peatlands and coastal wetlands. These are wet areas that hold a lot of carbon. Protecting biodiversity, and protecting the stewardship of indigenous lands, which is good for many reasons, but has various implications for protecting carbon and biodiversity. On the agriculture side, strategies include reducing fertilizer use, reducing cows and other ruminant animals, improving land management strategies for both cropland and grazing land. There are several different kinds of actions that can be taken on the demand side too, things like reducing waste in food supply chains, avoiding meat and dairy consumption, avoiding purchasing virgin wood as a construction material, so wood that is coming from certain sources. In addition to these strategies, monitoring the amount of emissions that come from the land is also useful for informing these strategies, since it's generally a bit more difficult to get precise emissions estimates for land use related emissions. So understanding what's going on. And here you're starting to see some connections to machine learning. So having talked through the strategies to reduce emissions in energy-based and land use sectors, let's turn to negative emission strategies. Negative emission strategies are strategies to actually reduce greenhouse gas emissions, usually carbon dioxide from the atmosphere. So this can include technological solutions like carbon capture and storage. We capture carbon dioxide either from exhaust in an industrial facility or directly from the air and store it underground. This does not really exist at scale yet. People are very fond of talking about it because it could magically solve everything. We don't have it working very well yet. It's very expensive. Negative emissions can also include solutions that enhance nature's ability to absorb carbon dioxide, things like planting trees, sequestering CO2 in soil, restoring peatlands, and so on. And this can also include biochar. This can also include biochar, which is a material that you get from processing plant materials and storing it underground. It's like a permanent way to store the CO2 captured in plants. Again, many of these things, especially carbon capture and storage and biochar, are somewhat expensive and speculative at present. I already talked a bit about afforestation, so planting trees. There can be advantages to that, but it is, again, risky, and it depends on exactly how you're doing it, how effective it is. Restoring natural ecosystems can be very valuable if you're sort of restoring them to the state in which they were in before, which is often a much sort of healthier and easier way to sustainably store carbon. Overall, negative emissions strategies are an important part of the kinds of actions that we need to take, but they face their own complications. They're not a substitute for other kinds of action. So that was a whirlwind tour through different kinds of mitigation strategies. In addition to sector-specific strategies, we can also think about cross-cutting strategies for mandating or incentivizing these reductions. So this often starts with setting targets on interfaces with policy. For example, at the international level, there are negotiations in the context of the UN that have caused almost 200 countries around the world to set voluntary targets for emissions reduction. Targets themselves don't do anything, of course. They need to be followed up by actually hitting those targets. We've seen spotty progress on achieving targets. This includes economy-wide regulations and standards and large-scale governmental investments. And for all that I'm a bit pessimistic about people hitting their targets, countries hitting their targets, these targets have been really useful. They have actually led to change at the national, regional, and local levels. It just may not be enough yet. So these targets have been extremely, extremely relevant. It can also include putting a price on carbon and greenhouse gas emissions more broadly to account for the costs of climate change and disincentivize greenhouse gas emissions from being emitted. This is itself a really big topic. It can be done through a bunch of different strategies like a carbon tax or a cap and trade system where entities can trade and sell a fixed number of emissions permits between. Not going to really get into it. But that was a whirlwind tour through climate change mitigation. Now let's turn to the last major axis of action, which is adaptation, responding to the effects of a changing climate. So climate change has some direct effects like rising temperatures, changing precipitation, etc. In addition, oceans have actually absorbed 30% of the CO2 we've emitted and 90% of the resulting heat increase. So thank you, oceans. If it weren't for the ocean, we would be feeling climate change a lot more. But that's also caused the water to expand and the ice to melt around the world. So that causes sea level rise, and the ocean is also acidified. All of these direct climate impacts lead to downstream effects like droughts and heat waves, more intense storms and flooding, wildfires, loss of ecosystem services, biodiversity loss, and the spread of disease vectors and pests, all of which we need to adapt to. So how do we actually deal with these things? The first step is by understanding the risks that we're going to face, meaning both the magnitude of impacts and the probability we might face them. For instance, this plot from the IPCC is looking at the expected changes in average annual mean precipitation globally at different levels of warming. Once you know what these risks might look like, the second step is strengthening adaptive capacity. So this involves building robustness to potential outcomes. For example, making sure your power grid doesn't black out when there's a big storm, as well as building resilience. That is, if your power grid does go out, making sure that you can bring it up more quickly. These are two sort of subtly different things. We need both. These kinds of strategies need to be applied across human and ecological systems, considering food security, water security, resilient infrastructure, ecological conservation and restoration. They have a lot of synergies with broader co-benefits in the UN Sustainable Development Goals. While these adaptation strategies in some cases take climate impacts as a given, there is also another set of actions, which I'm going to go through really, really quickly, which are extremely controversial. Solar geoengineering, an adaptation strategy that tries to slow warming directly or cool the Earth by increasing the Earth's reflectance, also called the albedo. The most common proposal here is to release sulfates into the stratosphere, which mimics what happens when a volcano erupts. Now, this is a difficult and contentious option due to uncertainties in its actual effects. Read that as it might kill everybody. Concerns that having this option might cause us to procrastinate on other strategies, like by feeling like we can just do this, which is actually really dangerous. People might feel less urgency about safer and more reliable options. Also, the fact that if you stopped doing this at any point, you would have really an even worse situation because you're just patching the problem, you're not actually fixing it. And also various governance issues, like what happens if all the aerosols blanket one geography and cause no agriculture to be able to happen then. So it's really generally viewed as a last resort, but I wanted to bring it up because you might have seen that as something that people talk about. Okay, so to wrap up, the main takeaways here are that we really need rapid action to address climate change. These axes of action include climate science, mitigation, and adaptation. And doing this right requires holistic thinking, for example, thinking about the intersection with climate justice and interactions with other sustainability goals. Now, many fields and sectors need to be involved in making these kinds of strategies successful. Various fields of science and engineering, also economics and social sciences, and public policy. And machine learning can potentially play a role in supplementing and strengthening these efforts. So now let's actually start talking about machine learning. Now we've seen overall what climate change is about, what its effects are, and broadly what's involved in addressing it. Let's dive into how machine learning can be relevant here. We're going to provide an overview in this section of the different roles that machine learning can play in climate action. We'll also look at considerations to bear in mind when evaluating and prioritizing applications of ML in the climate space. So there's this paper that Titipat mentioned where I and a large number of other authors wrote a detailed taxonomy and analysis of the different ways that machine learning can be used in climate action. And in the full paper, we identified opportunities for machine learning to play roles across the different areas and sectors, from electricity systems to buildings to transportation, land use, climate prediction, societal adaptation. There isn't time to go through everything. I do want to highlight a few themes we identified for the kinds of impact that machine learning can have. And I'm going to go into each of these themes with examples in the next few slides. So first, distilling raw data into actionable information, optimizing complex systems, improving predictions, accelerating scientific discovery, and approximating time-intensive simulations. Okay, let's dive into the first theme. There are many ways in which ML can help advance climate action by taking some huge raw data set and going through it to pick out actionable information, which might be too slow or cumbersome for a human to do at scale. Now, often in these situations, the raw data is a set of images, for example, satellite or aerial imagery, or a corpus of text. And so computer vision and NLP are often relevant, especially computer vision. The cases for natural language processing are somewhat more niche. I feel like I should say this because people nowadays want to use GPT for everything, and there are almost no applications of GPT that I know of in the climate space, unfortunately. So some examples. One example of where this role for machine learning comes up is in mapping deforestation in real time. Increasingly, ML is being used to parse satellite images to work out where forests are being cut down. And this can be valuable in guiding policy decisions, as well as interventions in cases where forests are protected. And mapping deforestation is also useful for verification in carbon markets where landowners get financial benefits if they can prove that they're conserving their land. And mapping carbon stock is a related task where ML for remote sensing is also being used. This means quantifying the amount of carbon that's stored in a forest or grassland or another area of land in order to better determine the value from an emissions perspective of preserving that land and price that in. Now, another setting in which ML is being used to parse raw data is in gathering information on buildings. There's very little publicly available information on what buildings are where and how much energy they use, which makes it difficult to shape policies. Using computer vision, it's possible to approximate the footprints and heights of buildings, which makes it possible to approximate their energy use. Now, I put a little M next to these examples because they're both example of mitigation, which again is reducing greenhouse gas emissions. Let's look at some examples from adaptation, which again is responding to the effects of climate change. So ML has been used, for example, to correct errors in global elevation maps so as to pinpoint coastal communities that are at risk from flooding. By working out the exact heights of different areas, these algorithms have made it possible to determine that hundreds of millions more people are at risk than had been previously thought. Now, and as an example from NLP, there's a lot of information in corporate financial disclosures that can be useful in informing climate policy decisions. For example, what risks companies anticipate from climate change. Training NLP models to pick out relevant passages, like topic modeling, has sped up the process of finding this information. Again, you don't need GPT for that. It's unreliable, and it doesn't actually have the functionality that you want necessarily. There are some applications of GPT. Just have to tell people this so much, especially journalists. So overall, we've seen ML algorithms can be very useful in distilling big raw data sets into actionable information that can guide policies or other kinds of decisions. Let's look at another theme. Let's consider settings in which ML can help operate complex automated systems more efficiently. A wide variety of algorithms can be relevant here, from classic optimization techniques to reinforcement learning. Examples: ML is being used to control heating and cooling systems more efficiently so they use less power. This is true both for smart thermostats in personal homes and also in the more challenging cases of large buildings and industrial processes. Increasingly, ML is being used to help optimize transportation schedules. For example, the timetable of the German railway operator, Deutsche Bahn, incorporates ML now. This can be useful in allowing different modes of transportation to interface smoothly with each other, like trains and buses or trucks, in the context of both public transportation and freight. And then ML can also be used to help guide demand response. That means certain activities that require electricity, but they're flexible on when you use that electricity, like charging an electric car or running a dishwasher. Maybe you can do those at different times. You can time them to occur when there's a surplus of power, more available, or when it's coming from lower carbon sources. Now, a note I do want to mention, in situations where machine learning is being asked to optimize a system, that can mean a lot of different things. The objective function is very important. In particular, it's not always aligned with climate action. For example, reducing cost may be something that you are asked to do, but it might not reduce greenhouse gas emissions. For example, if you're reducing labor costs by increasing transportation costs, moving something to a part of the world where labor costs are cheaper might actually increase emissions. It's also worth noting making a process more efficient can sometimes increase the amount that people use it. This is called a rebound effect. It can diminish the savings one gets from improved efficiency. It doesn't mean you shouldn't do it, but it can diminish the effects to some extent. Okay, moving on to our next theme. Machine learning can be helpful in improving predictions and forecasts across many different application areas. So a variety of time series analysis techniques can be relevant here, including Bayesian methods, sometimes computer vision as well, in settings with image-based data. As an example, on an electrical grid, the power being generated needs to match the power being consumed at each point in time. Now, fossil fuel power plants can largely be controlled to vary the amount of power being generated, but for solar and wind power, the power being generated varies from minute to minute, depending on how much the sun is shining or the wind is blowing. And ML is starting to be used to forecast how much wind and solar power will be available, including by using historical time series data and satellite imagery of clouds in real time. This makes it possible to use more solar and wind and less power from fossil fuels. Now, similarly, ML is being used to forecast the amount of demand for electrical power. The UK's national grid recently implemented ML algorithms that cut in half the error in their power demand forecasts. A while back, this was all being done by hand with lots of heuristics. For example, as I understand it, in the UK, people used to have a timetable of TV programs because every time a soap opera would end, there would be like a 10% spike in electricity consumption as the entirety of the UK got up and made a cup of tea using an electric kettle. And this would like noticeably increase electricity. So you had to take this into account. Just goes to show how many different factors you have to bear in mind and how much domain knowledge you need in order to address a problem like this. Okay, so as another example, this time relevant to adaptation, ML is being used to help forecast crop yield from satellite images in response to the threat that climate change poses to agriculture and food security. So our next theme is accelerating scientific discovery. Promise just one more theme after this. There are many settings in which new materials or other technologies can advance climate action, but perfecting these technologies takes huge amounts of experimentation, typically. In some cases, ML can speed up the process. It doesn't remove the need for physical experimentation, but helps design new experimental setups. So these algorithms can include generative models, active learning, reinforcement learning, and where chemical compounds are involved, they often involve graph neural networks. In the case of materials design, ML can be used to learn the outcomes of past experiments to suggest promising new materials. This can be valuable in the design of new compounds for batteries, photovoltaic cells, catalysts used in green energy applications. As another example, reinforcement learning methods were recently developed that can help effectively control plasma in experiments on nuclear fusion, which is a potential future source of low carbon energy. A bit futuristic and probably far in the future. For a final theme, let's turn to the ways in which ML is used to approximate simulations. Now, physics-based simulations turn up in a lot of different climate-relevant areas, and the calculations based on known physical laws are used, for example, in predicting weather and climate change, and they're really good, but they can be slow, and ML can be used in some cases to provide faster answers. Relevant ML methods here can include physics-informed techniques, which we'll get to, computer vision, and interpretable or causal methods, which again, we will get to. So as one example, climate models are complex ensembles of physics-based simulations, how variables like temperature and precipitation behave around the globe. And these models can actually take months to run, even on supercomputers. And even then, climate models normally operate at relatively coarse spatial resolution, like hundreds of kilometers, since higher resolution can be prohibitively computationally expensive. And so there are many different approaches being used here. We'll actually talk later about super resolution techniques to increase the spatial resolution of certain pieces of climate models. Now, in a totally different setting, ML is being used to approximate certain portions of car aerodynamic simulations in order to design more fuel-efficient vehicles. And then in the power sector, ML can speed up planning models used to simulate electrical grids. Again, they're based on domain physics. Okay, we've now seen a number of climate-relevant applications of ML across many different sectors and fields. ML has played roles in distilling data into useful insights, optimizing complex systems, improving predictions, accelerating scientific discovery, and approximating simulations. If you're interested in further details, I encourage you to check out the interactive version of our paper, which is available at this URL, where you can search for different applications by theme. Say, I am interested in this set of applications. I am interested in this set of ML techniques or this subject area. You can slice and dice the recommendations in different ways. Now, I want to go under the hood a bit and talk through how we actually came up with the applications to highlight in that paper. How do we evaluate and prioritize different opportunities for machine learning? There were a number of questions that we found to be very useful in shaping our thinking, and they're honestly still really useful for me now when I'm considering a new potential project. So first, is ML needed to address the problem? There are many urgent problems related to climate change where ML is not going to be helpful. There are also problems that have already been solved without using ML, and the existing solution may be perfectly fine. What's the scope of the impact, roughly? You don't have to work on problems that could reduce megatons of CO2. More modest gains do add up. But at the same time, maybe you shouldn't work on plastic straw reduction, not the best use of energy, of your energy. It's good to have at least some ballpark sense of how meaningful a problem is from a climate perspective. What is the time horizon of the impact? A ton of CO2 reduced now is much more impactful than a ton of CO2 reduced in 30 years, since the sooner we can achieve net zero, the lower the damage. This is one reason why planting trees, while important, is generally a lower priority than preserving the trees we have. I mentioned some other reasons why afforestation can be an issue, but just simply the time horizon is one reason. Working on technologies like nuclear fusion is similar because they're decades away from success and scalability, and that can be valuable, but it shouldn't distract us from nearer term solutions. So really think in terms of this as one factor. What's the likelihood that a solution can be found? It's very tempting to work on moonshots, that have some small probability of enormous impact. Oftentimes, it's better to work on problems with a high probability of medium impact, not small, but medium impact. Also, sometimes those moonshots actually have a long time horizon, which we've seen is less ideal. Can a solution feasibly be deployed? The best algorithm in the world isn't going to have an impact if nobody uses it. Sometimes ML works, but it isn't scalable in the relevant setting, maybe because of hardware costs, expertise required to run and maintain it, or access to annotated data. If you don't have those things, then your innovation is not necessarily going to be impactful. What are the potential side effects of deploying the candidate solution? An optimization algorithm might reduce greenhouse gas emissions, but increase other human costs. A system for gathering data on vulnerable populations could be co-opted by bad actors. Depending on the situation, it may not be feasible to avoid all the negative side effects, but where possible, they should be recognized upfront and reduced. Who are the relevant stakeholders who are involved in or affected by the application? They may have constraints or requirements that need to be built into any viable solution. We'll talk more about this later. It's through the eyes of these users that an approach should be judged. Because again, you need to actually have your algorithm be used. And then finally, I'd like to highlight a number of considerations to bear in mind when thinking about the overall space of ML applications in climate action. So first, let's remember, machine learning is not a silver bullet. It's not going to magically solve climate change. It's only one of the many tools we need, and it's not applicable everywhere. It should never replace or distract from other actions involved in climate action. Secondly, some of the most impactful and interesting applications aren't flashy. For example, detecting failures in railroad systems doesn't receive as much press as autonomous driving. But from a climate perspective, it's probably actually much more beneficial. I'll actually talk about this later. So sometimes to find these non-flashy problems, you actually have to dive deeply into understanding what's needed in a particular area of application. They don't necessarily make the press. It's also worth noting that while state-of-the-art methods can be useful in many cases, and something we'll discuss at length later, in other cases, simpler methods may be enough. You shouldn't leap to using transformers when linear regression will do the trick. In my own research group, we try to pick problems where we think ML innovations are going to be necessary, but we still start out with the basic methods because sometimes those turn out to work well. When thinking about climate applications of machine learning, it's essential to conceive of them as collaborations, including both ML experts and domain experts. Often other stakeholders who are involved in deployment or are affected by the technology should be included too. These kinds of partnerships are important to make sure that the algorithms aren't solving the wrong problem. Can't tell you how many times that happens. It's really unfortunate when you discover it after you've already done the work. It's important to make sure that you incorporate domain knowledge. The stakeholders who understand the problem have a lot of knowledge. If you can build that into your algorithm, you're saving yourself a lot of work. Partnerships are also key to ensuring that there's a pathway to impactful deployment, making sure that any considerations relevant to deployment are built in right from the start. And then lastly, equity considerations are fundamentally important, including who's building solutions, what problems are prioritized, and how these problems are being worked on. So empowering a diverse and global set of stakeholders is essential to ensure the technologies are owned by the people affected by them, rather than reinforcing existing power imbalances across countries and institutions. I say that as a researcher at an institution that has a lot of resources in a country that has a lot of resources in machine learning. Related to the question of who is the question of what is being worked on, since problem priorities often reflect existing inequities within ML and technology more broadly. So for example, machine learning to fight wildfires, which are a problem in North America, Europe, and Australia primarily, that tends to get a lot of attention and funding more than maybe machine learning to fight locusts, which affect East Africa, the Middle East, and India, even though both problems are extremely important and are exacerbated by climate change. And then how projects are being worked on is also important. Data imbalances between regions or between communities within a region can mean that ML solutions are only applicable to a subset of the population, or that algorithms are most effective within data-rich areas. Ideally, ML for climate will serve to improve equity, but this takes a lot of active work at the level of project design and management. I'm going to pause for a moment. I've been going really full tilt. Are there any questions that people have? I'll have another few minutes at the end of this session.
Okay. So maybe I have a question. So it seems like from your tutorial right now, you're actually looking at applying ML to fix, but maybe ML is the problem. With large language models, the cost of training that it might be more.
Yes.
Yeah.
We'll get to it, second part.
Oh, okay.
Hi, as someone who's concerned with the application of ML and the amount of electricity it can use up, I have some questions like how would you evaluate whether an ML is needed in a certain application when like the common people and the pattern established by a human might be sufficient enough in certain areas?
I'm sorry, I don't think I caught the question. Could you repeat it? I apologize.
Right, okay, this is gonna be hard for me to recite again.
I'm so sorry.
It's okay, it's okay. My question is that in certain applications, right, how would you evaluate whether a machine learning model would be needed in comparison to like the common human behavior that could actually be efficient enough in that use cases?
Yeah, it's a great question. I mean, it's a lot of iteration with the people who are using the current strategies and understanding what their pain points are. Like, what are the people who are using current strategies held back by? Are they held back by not having enough processing in real time of, you know, where the deforestation is happening? Do people have to go through manually and track a lot of maps? Do they not have enough people to do this? Is this something that ML could even do? Sometimes people don't know where ML could be useful on the side of the domain stakeholders. And sometimes the ML people don't know what the domain stakeholders actually need. So you need to meet in the middle, and it takes a lot of confusing conversations sometimes. There's oftentimes literature that's started to build bridges between different communities, and there are sometimes organizations, we'll get to that at the end, to how to sort of step into bridge building roles between different fields and sectors. Definitely a challenge to work out where machine learning is relevant. These questions that I asked are not necessarily easy to answer, but they should be in your head, even if you can't answer them perfectly in every case. One more question? Or not, I can move on. We'll have plenty of time for questions later. I have a lot more content. Oh, sorry, is there another question?
Nope, I don't think so. Yeah, we can continue. Yeah.
Okay. Cool. So let's go to research challenges. One moment, so just set up my slides again. Okay, so the overview you just saw of machine learning and climate action represents a mix of projects that can be implemented today and novel research challenges for the machine learning community. And I don't want to make you think that everything is a research challenge, because a lot of applications of machine learning can just be machine learning used out of the box. But given the context for this summer school, I want to talk about how there are some interesting research challenges for the machine learning community. During this part of the tutorial, we're going to dive into a few of these, specifically the areas of physics-informed and robust ML, interpretable ML and uncertainty quantification, and generalization and causality. This is not an exhaustive list, and it's not mutually exclusive either. These are just some core paradigms of ML research that might be particularly fruitful. And we're going to see in each of these cases how thinking about climate-relevant problems actually can shape the directions of computer science research and suggests important problems for working on from a computer science perspective. So let's start by talking about physics-informed and robust machine learning. Now, many climate change related sectors deeply involve science and engineering. For example, climate science, engineered sectors like electricity systems, buildings, transportation, and industrial sectors like heavy industry and agriculture. And challenges in these areas include a combination of modeling problems, like modeling climatic processes or simulating wind flows through cities, optimization problems and control problems like managing devices on the power grid or controlling agricultural equipment, and accelerating discovery of things like alternative fuels or new low materials construction techniques. And in these areas, there are a lot of directions associated with merging the knowledge or requirements from these domains with the development of machine learning tools. A major class of approaches here include physics-informed approaches. These approaches involve designing ML methods that employ physical knowledge or priors within the ML workflow. For example, in the data, the loss functions, the architecture design, in the case of deep learning, to improve performance, or also to improve attributes that might be relevant, like data efficiency. So the reason we tend to want to pursue physics-informed ML is they can blend the strengths of traditional physics-based and ML approaches and potentially mitigate their weaknesses. So here's a really high-level chart showing that. Physics-based models are good at efficiently leveraging existing knowledge in a way that doesn't really depend upon gathering any data. And their outputs tend to be more transparent and less brittle. That said, these models struggle if their physical assumptions are incorrect, and they're slow to run. Often it means solving lots of coupled differential equations, for example. Now, pure ML approaches are often data inefficient, physically inconsistent, black box, and brittle, but they're really good at learning about the reality of the underlying system from data, and they're fast to run. And this has led to a lot of work in hybridizing these kinds of approaches. Ideally, that has all of the successes, but none of the failures. So for example, in climate science, which again means studying the climate, atmospheric models are very time-intensive to run, which means you can't afford to exactly encode all the fine-grained atmospheric physics that you would ideally encode. Like in practice, people cut corners. We know how the atmosphere works, but solving it exactly just takes too much time. And so we approximate things already in climate models. Climate scientists try to figure out ways to cheaply approximate these fine-grained processes, but still respect important laws like conservation of mass, energy, etc. Recent work by Böckle et al. Has said, let's write down the conservation laws we want our approximator to satisfy and embed a module into a neural network architecture that ensures these conservation laws are satisfied. This allows you to learn a neural network-based emulator for your fine-grained physics that satisfies your essential constraints. And we're going to see an example of my own group doing this in the context of downscaling later on. So another related example. Another example that comes up in the domain of buildings, we often want a cheap model of how the dynamics of a particular building actually look in order to either enable the implementation of simulators for RL, reinforcement learning, or enable control strategies like what's called model predictive control that depend on some knowledge of the underlying dynamics. Now, one approach that's been pursued is to try to learn a differentiable surrogate for these physics, because you can't actually differentiate through the physics equations of how energy flows within a building in order to train a machine learning model. For example, Dragona et al. Observed there's a particular block-based structure exhibited by certain building thermal dynamics models. Again, all of this is about, in this example, is modeling how heat flows within a building. So you can try to lower the energy required to heat and cool buildings. And by doing this, you can learn an emulator that combines some of the approaches from some of the approaches from ML with some of the constraints of physics. Since it's differentiable, you can embed this into a broader differentiable workflow for learning control policies. It's like a really high-level overview of some different ways that this can work. There are many potentially fruitful directions in the area of physics-informed ML for climate change. Do want to also note that the papers I was just describing deal with linear constraints. There are many cases that call for more complex constraints. These include things like the physics of the power grid, which is non-linear, and I'm going to get into that a bit later, discussing some of my lab's own work. The resultant neural network architectures are often harder to optimize if you're working with these nonlinear constraints. And there's some related directions in improving physics-informed neural network training. It exists in addition to physics-informed algorithms. There are also potentially interesting directions in structuring data in a physics-informed way. For example, representing Earth systems data using a cubed sphere representation instead of a grid representation. Perhaps that better captures the Earth shape. Many authors have found this. So thinking about how we're structuring our data. And then finally, there are a lot of situations where one wants to generalize to unseen scenarios. For example, predicting nonlinear dynamical processes that are changing over time. There's a school of thought that combining machine learning and physics can be one way to approach this. Okay. These are some of the directions you might want to go in if you're interested in exploring this. So switching gears, another major set of approaches here involves robust and safety critical machine learning. Here we want to use machine learning to actively optimize or control a system, but it needs to satisfy various kinds of system requirements. For example, engineering constraints or robustness constraints to enable it to be deployed on that system. Safety critical systems like power grids, if you don't satisfy these engineering requirements, that could mean you have a blackout. And blackouts cause huge amounts of losses, like economically, but also losses of life. And nobody will deploy any algorithm that has a risk of leading to a blackout, or they shouldn't. So how do you build in these kinds of safety or robustness guarantees? Now, when I'm talking about robustness, this is a word that comes up a lot in machine learning, but there are actually lots of different definitions. And the definitions that are different in the machine learning and the climate context. So there's adversarial robustness. That's often used in the deep learning literature. How do you learn deep learning models that are robust to perturbations of their inputs? In the reinforcement learning literature, there's a notion of safe RL. Can you create an RL algorithm that doesn't leave some space of states that have been determined to be safe, stays in safe places? And then on the engineering side, for example, in power systems and buildings, there's a combination of robustness, which is called Lyapunov stability. And that comes from robust control. If I start my system in a given state, can I provably make sure my controller brings the system to some kind of equilibrium over time? Now, these are just some illustrative examples, different kinds of robustness. It's important to know that to check that you're implementing the right notion, because these are all really useful notions, but sometimes useful in different contexts. So one line of work that tries to build reinforcement learning methods for the control of components on power grids in order to better enable the integration of renewable energy. So this kind of work is meant to be employed on power grids. So the notion of robustness you need is this Lyapunov stability notion. It's common in power grids. So one way of doing this is to design neural network architectures that internally enforce Lyapunov stability. For example, structuring the neural network controller to enforce in this case, monotonicity property that ends up implying stability. So there are various different papers that are cited here. So for example, Donte et al. Used implicit layers to enforce Lyapunov stability constraints. Another approach, this Rutten et al. Paper, is to mix the outputs of a traditional robust controller and an untrusted standard RL algorithm in a way that gives you both performance and robustness. And overall, this is just saying, let's build an RL algorithm that satisfies an engineering-based notion of robustness. Okay. So it's also possible to do the exchange in the other direction, where we translate notion of robustness from machine learning to climate-relevant fields. And so this paper by Donte et al. Uses techniques from the standard sort of adversarially robust deep learning literature to robustly optimize power grids under the threat of many different failures, like many different lines go out across the power grid. And so this is called N-case security constrained optimal power flow. And if you were trying to actually go through all the scenarios by hand, this would be prohibitively difficult because there's just so many things that could go wrong in a power grid. But if you write this as adversarial robustness from a deep learning perspective, you can actually use it, solve it heuristically using machine learning techniques. And this allows you to actually go to a realistic scale of power grids, which hadn't been done previously by power grid operators. So to summarize all these different things, there are many fruitful directions for merging physics and engineering knowledge with machine learning approaches. These can have benefits across many different climate-relevant sectors and areas. And this includes physics-informed approaches, where there are a lot of directions to, for example, accommodate new and more complex physical constraints, approaches in robust and safety-critical settings, where there are many opportunities to implement, exchange, combine different notions of robustness. They're used in different domains. And across all of this, a key takeaway is that you really need to understand the climate change relevant domain in order to understand the kinds of physics and engineering constraints that are useful to satisfy, and how this can lead to new methodological directions for machine learning. So that's the first set of research challenges in ML that I wanted to talk about. Now let's talk about interpretable machine learning and uncertainty quantification. So many situations in climate change mitigation and adaptation require trust, stakeholders trusting one another and trusting the systems that they're using, and robust decisioning. So from scientific understanding and predictions of climate change to monitoring, reporting, and verification of the emissions and climate change impacts. So governments that are using satellite imagery processing tools, to early warning and emergency response systems in the case of extreme events, to policymaking. There are tools that engage directly with the policymaking process, planning of infrastructure, and understanding innovation and technology landscapes. All of these require various kinds of decisions to be made where the stakeholders making the decisions really want to have visibility on how a decision is being informed by an algorithm, and also what kinds of guarantees exist in the system. So many different aims here. In the interpretability heading, we have oversight. In many different settings, we need the ability to have regulations surrounding algorithms and recourse in case the algorithms go wrong. We need the ability to intervene and override a model output if the machine learning system is going wrong. And we need to be able.
Hi, David.
Hello, folks.
Yep, sorry, yeah. Our meeting gets interrupted, so we are back. Yeah, all right.
Everything good?
Everything is good. Yeah, good.
Okay. So let me share slides again. Here we go. Okay. Yeah, so we need to be able to potentially insert interventions into the model itself if there's something in the middle of the model that needs to be debugged. Credibility is also really important. You need to be able to persuade people to actually use your technology, right? Many people will not use a machine learning algorithm unless they have some idea of how it's making decisions and what's going into it, what kind of guarantees exist. Scientific discovery, working with and expanding domain knowledge can be really useful. It can be an opportunity for interpretability, where if you uncover some mechanism for scientific understanding in your machine learning algorithm, that can actually contribute to scientific knowledge. So these are all goals of interpretability, understanding how an algorithm is making a certain decision. Uncertainty quantification is a related goal. This can be useful in assessing risks. So understanding how much one should rely on decisions and how one can be robust to certain kinds of failure. And in avoiding overconfidence and boosting credibility from a communication standpoint, if you say, the algorithm predicts this, but it's only 50% confident, then stakeholders will not be so surprised if it is wrong. Oftentimes, interpretability and uncertainty are really, really poor in especially deep learning-based models. Interpretability, oftentimes there's no interpretability or very limited interpretability. Uncertainty quantification, oftentimes there are probabilities, but they're not really very well calibrated. So here, let's look at some examples of where these kinds of considerations occur. Ocean subgrid scale modeling. So here, what we're trying to do is we're trying to model stuff going on in the oceans. Subgrid scale modeling just means you have a low res prediction of what's going on in the ocean, and then you want to increase the resolution of that by modeling the finer scale processes. Now, the way in which these particular authors did this, sorry, I think it's out of date, I think it's been accepted somewhere, is that they actually discovered equations governing the subgrid processes. So they actually were able to predict equations that weren't known to ocean scientists, which is really cool. So not only was it able to do what was wanted by the ocean scientists, it was actually able to help create science that could be used down the road. The second example that I want to touch on here is in crystal structure phase mapping. So this is for solar fuel materials. Requires this process of separating out different X-ray diffraction patterns into particular source signals. You have like different patterns that are coming on top of each other. And it is a pattern demixing problem, like signal separation, or many different problems like this. So the goal here is to use an unsupervised pattern demixing problem, unsupervised pattern demixing approach, where in this case they use these deep reasoning networks, which also exploit some prior knowledge about rules governing the mixture of crystals. So this engages with a physics-based, physics-informed machine learning section. And then they construct an interpretable latent space that can then be learned in an unsupervised setting. So the usefulness here is because it is interpretable, you can engage with the algorithms. There's much more interplay between physics-based approaches and learned approaches. The interpretability sort of interfaces with the physics-grounded nature of the approach. Here's another example. Computer vision is very useful across various different kinds of ecosystem monitoring. The habitats of species are changing rapidly with this changing climate, and monitoring species is really important. One of the ways you monitor species is with the ability to just identify species from photographs. In this case, these are photographs taken by citizen scientists, so people going out there and photographing birds. In this algorithm, the goal is not just to predict a species of bird, but to say why. And this is really useful in informing, in both helping teach people things and also making it be a more accountable system that is more compelling to the ecologists who could be using it. So saying this part of the image looks like this prototypical part on a reference image, and this part looks like this, so I think it's the same species as this reference image. And the final example that I want to touch on is more of an uncertainty estimation setting. So here we're looking at residential net electricity load, where we're trying to predict the net load, so power, the demand for power minus the power being generated. And there's a lot of uncertainty involved here from all kinds of things, including whether people are watching a soap opera, as I mentioned before, whether there is a cloud going over the sun, which is reducing the power being generated by the solar panels, etc. Lots of different uncertainties. And so the approaches here have combined Bayesian theory with deep LSTMs for probabilistic day-ahead forecasts, and having these kinds of probability estimates for is the load going to be within this interval and this interval is really useful in order to make sure that you not just can accommodate the load that's likely to occur and produce enough power to meet that demand, but also have a bit of a buffer. How much of a buffer you need is informed by how tight your uncertainties are. Okay, so some takeaways overall here. Decision-making and discovery are crucial for many areas of climate action. And in these kinds of contexts, there's a need for interpretability and uncertainty quantification. There are domain-specific goals that drive a specific notion of interpretability used. So in every one of these applications, there's sort of a different notion of interpretability. And the lack of documented use cases from practice where interpretability and certainty quantification in ML there are relatively few settings that are driving ML innovation. And so thinking about climate relevant action spaces is really helpful in grounding algorithmic innovation. Sorry, I didn't word this well on the slide. And the challenge here is, again, really user-focused method development, because interpretability and uncertainty quantification are very user-focused metrics. So understanding what the user needs. And the final theme for research innovation that I want to talk about here is in generalization and causality. So there are many different ways in which the concept of generalization occurs in machine learning. Some of these are generalization across different tasks, generalization under concept drift, and generalization from limited data. Let's look at each of these in turn and how they turn up in climate contexts. So first, generalization across tasks. This turns up frequently in climate mitigation and adaptation. There's a similar task that needs to be performed across multiple geographies or communities, and where the task and or data take somewhat different forms. So for example, classifying land cover across in France might be different from doing so in Brazil. There are different forests in those two places, and they look different because they're different trees. Likewise, in predicting the demand for electrical power, the patterns of electricity consumption might vary greatly between regions or even between communities in a single region. In tackling these kinds of problems, two possible strategies are to derive data embeddings and features that can be transferred readily between different tasks, or to build meta-learning algorithms that can learn each new task rapidly. As an example of the first strategy, let's look at an approach for deriving task-agnostic features for satellite images in an unsupervised manner. So we've seen many climate-relevant problems involving satellite images. Rolf et al. Present an approach called mosaics, which is based on the idea of random kitchen sink features. They take the idea of satellite images and convolve them by a large number of randomly cropped image patches. This is like a random convnet to get a set of unlearned feature maps. And they then run these through a nonlinear function. They sum over the spatial dimensions to get a very high dimensional feature vector that represents every satellite image. All of this is unsupervised. It doesn't actually involve any tasks. And when a task comes along, it is a simple regression from the mosaic features to whatever the desired output is. So actually, this approach performs almost as well as fully supervised ResNets trained on the individual task. And it significantly outperforms transfer learning from neural networks that were trained on other tasks. And there's a hope that this kind of approach can be really transformative in allowing researchers and stakeholders, especially like under-resourced researchers and stakeholders, to quickly spin up decent remote sensing algorithms with much less data and much lower computational cost. Now, let's consider an example. Oh, no, sorry, I moved the example of meta-learning to the other discussion sections. We'll get to a meta-learning example later with task-informed meta-learning. And then another strategy that's often used in these kinds of contexts, or should be, is to simply treat the tasks separately. So I just want to highlight, you do not necessarily have to have a foundation model that works across every single task. I cite this particular paper because there is sometimes it fits into the overall paradigm of machine learning values that a one-size-fits-all approach is often the way in which machine learning culture sort of pressures you to go. And in many cases, there may be a more useful and equitable solution in practice to treat every task separately and come up with problem-specific solutions to those individual tasks, rather than coming up with a one-size-fits-all approach that's actually worse on a lot of different tasks. So the second kind of generalization I want to talk about is generalization under concept drift. What that means is the data or the task is actually changing. So not surprisingly, this turns up quite a lot in climate change. A changing climate means changing data. Machine learning methods trained on climate and weather data from the past or the present often fail spectacularly on simulations of the future because the future data is different. The climate's changing. That can also be relevant in tasks that are affected by climate change. For example, agriculture looks different as temperature and rainfall patterns shift. Species distributions change. So biodiversity predictors can become out of date. The supply of solar and wind energy changes along with weather patterns. Strategies for coping with this vary a lot depending on the particular setting. In areas like climate science, physics-informed models, which I talked about earlier, can be very useful since the physics governing the climate doesn't actually change, just the inputs. So that can be useful in dealing with concept drift. Combining physics and ML can make the ML methods generalize much better under non-stationary data. Another strategy can be to use synthetic data to train machine learning models. For example, if one has access to reliable physics-based simulations. A third kind of generalization is generalization from limited data. This can manifest in a couple of different ways. Data distributions may be long-tailed with a large number of classes or scenarios that occur only rarely. For example, identifying animals from photos, some species may be much rarer than others. Alternatively, the goal of a task might be actually predicting some rare events like wildfires or hurricanes, and there might be limited data for those situations. In long-tailed data distributions, algorithms can be designed specifically with data imbalance in mind, or for the paradigm of few-shot learning. In the case of identifying extreme events, you can use unsupervised or self-supervised learning. That's often methods that are used in the context of anomaly detection. So let's look at some examples. First, what a long-tailed distribution can look like in a climate-relevant context. So let's consider the iNaturalist dataset from Van Hoorden et al. This is based on data from the citizen science platform iNaturalist, where thousands of people from around the world have submitted photographs they've taken of animals, plants, other organisms. And these photos are identified by experts, and they're used to understand global biodiversity loss, but manual identification is slow. Increasingly, ecologists are using tools from computer vision to scale up the identification. Now, the iNaturalist dataset has almost 1 million images, and these represent some 5,000 species, many of them extremely similar looking. This is still just a fraction of the variety of species being photographed, and there's a lot of work left to do, but this is a curated dataset from within a much larger pool of data. The data is very long-tailed. Even in such a large data set, you can see in the plot some species are particularly common, and they have thousands of examples, whereas less popular, less photogenic, or less common species have maybe less than 50 examples. This is increasingly popular benchmark used to test highly imbalanced visual classification and localization algorithms. Let's now turn to the setting of extreme events. So one example of an extreme event is avalanches. There are relatively few annotated images of them. There are, however, many satellite images of places where you might have an avalanche, but there isn't one. So, a mountainside where there is no avalanche. So these authors leverage this in a self-supervised approach to detect avalanches, essentially as anomalies in satellite imagery of mountains. So specifically, they train a variational autoencoder on this imagery. They compress the imagery, reconstruct it, and they find the images that have high reconstruction error correspond to avalanches. since these are so poorly represented in the data that the VAE doesn't know how to represent them. This is a really cool way to do anomaly detection. Find out what your algorithm hasn't learned. That's the anomaly. In complex physical systems like climate and weather, ML can provide significant value by helping improve causal models. I'm actually going to skip over the causality section, though, because we're running short on time and I want to leave time for questions. So you can ask me about causality if you want. Some takeaways from this section. There are important climate change applications that can lead to interesting methodological challenges. And the generalization-related challenges that I talked about can arise from geographic variation across tasks or data, non-stationarity, so changing data, and imbalanced data or rare events. There are also causality-related challenges, which I'm not going to get into, but I'm going to leave a few minutes for questions, and then after that, we can have a break. Do folks have any questions?
Hello. So I just like thanks for the presentation, and given the diversity of problems that can be solved in climate change based on ML, I wanted to ask you how did you prioritize which problem you tackle on first and after and so on?
How do you choose which problem to tackle? So I'm going to talk about this in a lot of different ways sort of throughout the talk. And I'll have a section on this at the end, but I would think about where you are interested and where you have leverage. So leverage could mean you're expert in a particular set of techniques, or that you know people who are in a relevant field, or you have experience in that field. Like maybe you work at a company that does some agriculture stuff. Maybe you have leverage, therefore, in machine learning and agriculture. Think about the particular people, the particular problems you've engaged with, that you find interesting, that you have knowledge of. Don't think about what the most impactful thing is. There are so many impactful things. There's no one thing that's more impactful than everything else. Think about where you can make a difference with your skills. This is the theme for overall this entire talk, too, because machine learning isn't the only set of tools relevant to climate action. If I were talking to a bunch of policy people or artists or chemists, I wouldn't be saying you should use machine learning. I would be saying you should use policy or art or chemistry to fight climate change, because those are powerful tools as well. So think about your particular niche and the tools that you have, even within machine learning, and the leverage that you have in engaging with different problems using those tools.
Thank you.
Questions? More questions back there, or? So I think I have like a short question. I think you
Sure.
mentioned a little bit on like how people can get into the field, right? So I think as like a local community, or let's say in Thailand, right, it's kind of a little bit hard to, I think, have like mentors in, let's say, like AI for climate change, and like we only have like some specific problems that we probably know, like agriculture, they're like really close to Thailand, but yeah, I mean, I guess like I asked the question for maybe like for the newcomers, maybe like for the people.
There's an entire section that I have on this at the end.
Oh yeah, all right. So yeah, all right, sounds good.
I put it at the end so that it would hopefully be the last thing that everybody remembers.
Got you. Yeah.
Maybe that was a bad idea because everybody's going to be asleep. Let's take a break. Come back in 10 to 15 minutes. What do you think?
Yep, that's good. Yeah, 10 minutes break, and then we are coming back at 10 a.m. I mean 10:40. I mean in Bangkok time zone, not Montreal, but yeah. 10 minutes.
See you all at 40 past.
All right.